I welcome you to the session How Researcher Can Use Statistical Inferential Methods Effectively. I am Professor Jitesh Thakkar, Dean Academics and Professor Logistics and Supply Chain Management at Gati Shakti Vishwavidyalaya. It is India's first and only university in the transportation and logistics sector. I am ex-professor IIT Kharagpur. I would like to introduce you about this channel. Professor Dr. Jitesh J. Thakkar is the name of the channel, and currently it has two playlists: faculty and student development and logistics, supply chain and infrastructure projects. You can scan this QR code on the right hand side to explore the intellectual content on this channel benefiting students, faculty, and industry professionals at large. This playlist provides insights into the various facets of teaching, research, experiential learning to see that faculty and student can have 360-degree development in higher education institutions. It is providing the inputs on pedagogical skills, utilizing digital technology, creative thinking, promote research excellence, productivity by providing training in research methodology, data analysis, and experiential learning through projects, internships, and exposure to real-world problems. This platform explores critical dimensions of faculty and student development for enhancing the capability and quality of the most important stakeholder of higher education, that is, faculty and students. About my university, Gati Shakti Vishwavidyalaya, it is created in 2022 by the Act of Parliament. It is established by Ministry of Railways, and it has a focus to contribute in the entire transportation and logistics sector, including rail, road, water, aviation, ports, and shipping, with a focus on all three dimensions: transportation, infrastructure, that is technology, management, that is services, and policy, that is regulation and reforms. It leverages the utilization of state-of-the-art infrastructure of centralized training institutions of Indian Railways. The vision of the university is very much in line with the 21st century aspirations of the society, industry, and nation. GSV is an innovation-led, industry-driven university with a mission to be best in the world, effective collaboration with industry and stakeholders, and imbibe and internalize professional ethics and culture to foster lifelong learning. University offers programs with a focus on all the modes of transport in BTech, civil engineering with a focus on rail engineering, similarly BTech in electronics and communication, BTech in mechanical, electrical, all with a focus on rail engineering, BTech in artificial intelligence and data science, with a focus on transportation and logistics, BTech in aviation engineering, MBA in logistics and supply chain management, MBA in ports and shipping logistics. University also offers the programs for working professionals for their upskilling and improve the competitiveness of the entire transportation and logistics sector. The programs are offered in a hybrid mode: MTech Intelligent Transport System, MTech Rail Engineering, MTech Bridge and Tunnel Engineering, MTech Roads and Highway Engineering, MBA Logistics and Supply Chain Management, MBA Metro Rail Management, MBA Multimodal Transportation, MBA Aviation and Operations Management, PhD in Engineering, and PhD in Management with a focus on transportation and logistics sector. This video exchanges the views on how researcher should utilize statistical inferential approach effectively. I am happy to share my contribution in statistical research. I have published a textbook on structural equation modeling application for research and practice with MOs and R with Springer. It is an international edition, and this book typically introduces the structural equation modeling with variety of applications, and also it talks about the type of structural equation modeling like latent growth curve model, Bayesian, partial least square SCM, hierarchical SCM. Then it gets into the technical aspects of the SCM, the steps involved, what is the conformatory factor analysis, what is the path analysis, and mathematical specifications of structural equation modeling, and most importantly, sample size consideration in SCM. Third, it defines the procedural steps in structural equation modeling. Then, chapter 4 presents total 4 applications in healthcare, marketing, productivity, job satisfaction, and HR policies using the MOs. Similarly, the chapter 5 presents the applications of structural equation modeling with R for student performance and teaching pedagogy model and productivity model. And finally, the book concludes with chapter 6, application of SCM and some of the frequently asked questions. In addition to the textbook I have contributed in structural equation modeling, there are 2 papers published in high quality impact factor journals, Sustainable Supply Chain Practices and Empirical Investigation for Indian Automobile Industry. The paper is published in Production Planning and Control, year 2016, volume 27, number 1, pages 49 to 64, by Gopal, PRC, and Thakkar, JJ, myself. Similarly, we applied structural equation modeling for direct and mediation effect of supply chain complexity, drivers on supply chain performance. It's an empirical evidence of organizational complexity theory analysis. The paper is published in one of the most reputed journal, International Journal of Operations and Production Management, in year 2022, volume 42, number 6, pages 797, 825, by Chand P. Kumar A. and myself, Thakkar JJ, and Ghosh KK. This video will help you to gather insights on some of the most critical aspects, methods of statistical inferential approach, and the most basic is to represent your data in the graphical form. Then little brief and understanding about the hypothesis testing, regression analysis, analysis of variance, structural equation modeling, principal component analysis, PCA, factor analysis, correspondence analysis, and cluster analysis. These are most widely methods in the domain of statistical inferential research. So briefly, when we talk about the research proposal flow chart, typically as a part of your PhD you develop, then we begin with the introduction, we try to explore the what, why, and how about the topic. Then we get into the details of literature review to understand why and how and what are the research gaps emerging. Then we figure out the research issues, objectives, and then we choose the methodology. Then we go for the primary data collection, statement of limitations, and then we draw the conclusion keeping what, how, and why in mind. So typically the step 3 is methodology, selection of the methodology. Subsequently, we apply the methodology, and the data-driven research, empirical research, has a very wide application across management, engineering, social science for drawing the generalized conclusions, and that is where statistical and inferential techniques have a special role to play. If we just look at the graphical visual representation of the data, then we look at the data type, then what is the purpose and audience, then data volume and granularity, then comparison versus distribution, trends and patterns, clarity and simplicity, interactivity, tools and resources. So typically, I use this consideration to select an appropriate method for the data representation in a graphical or visual form. So typically, there are various methods available, techniques available to represent your data. Let it be bar chart, let it be histogram, box chart, Pareto analysis, pie chart, and all this helps me, the spider diagram, all this helps me to understand the distribution of the data, understand hidden pattern within the data, and typically how my data within the cluster or within the typical organization looks like. This helps me to further address some of the issues with the help of detailed inferential analysis, which are most critical, and this provides me the bird's eye view of my data. So let's look at the inferential methods. My inferential methods are divided into univariate methods, bivariate methods, and multivariate methods. Univariate techniques or methods you can divide as per the nature of data. You may have metric data, also known as quantitative data, which is quantifiable, measured, typically numerical data, or it can be non-numeric, non-metric data, which is qualitative data, subjective opinion, cannot be quantified or measured numerically. So when I look at the techniques, inferential techniques within univariate, within metric data, I can use one sample t-test or z-test. If I have two or more samples, I can go for two group t-test or t-test or z-test, one-way ANOVA, or I can go for paired t-test. If I look at the non-metric data, the classification, then one sample I can use frequency, chi-square test, KS, runs, binomial, two or more samples if I am investigating, and if those are independent in nature, I can go for chi-square, Mann-Whitney, median, KS, KW or if they are related, then I can go for sign test, Wilcoxon test, McNamara test, chi-square test, and so on. Similarly, if I look at the classification of bivariate analysis, then I can broadly divide my inferential techniques into descriptive analysis and inferential analysis. I can represent it in the form of two-way table or graph that already we discussed. So you have two-way tables, percentage distribution, frequency distribution, box plot, scatter plot, bivariate line chart, bar chart, bivariate chloropath map. All this falls into visual representation. If I look at the inferential analysis, I can broadly classify into parametric and non-parametric. Parametric, I can use t-test, chi-square test, regression analysis, one-way ANOVA. Non-parametric, I have Wilcoxon Mann-Whitney test, Kruskal Wallis test, McNamara test, Spearman rank correlation, Moods median test, Godman Kruska's gamma test, chi-square goodness of fit test, and Kendall correlation. So this is the broader classification of bivariate analysis. I can also look at the classification of multivariate analysis techniques, which are broadly classified into dependence method and interdependence method. Dependence method includes one dependent variable, or it can have multiple relationship structural equations, or it can have several dependent variables. If it has one dependent variable and my data is metric, I can go for multiple regression and conjoint analysis. If the data is non-metric, then I can go for discriminant analysis and logit. If I have several dependent variables, then metric data, I will go for ANOVA and canonical analysis. For non-metric, I will go for canonical correlation dummy variable analysis. If I look at the interdependence methods, then metric data, I have factor analysis, cluster analysis, and for non-metric, I can use metric MDS approach or non-metric MDS and correspondence analysis. Broadly, if we see the understanding what is dependence or interdependence techniques, statistical techniques, then dependent techniques typically focuses on relationship between independent and dependent variables, cause and effect, while the interdependence techniques analyze how variables influence each other without a predefined dependent variable. So dependent techniques, it examines the relationship between one or more dependent variables and their independent predictors to measure how change in independent variable can affect the dependent variable. Multiple linear regression analysis, discriminant analysis, logistic regression, canonical correlation analysis, they all fall within the umbrella of dependence techniques. So assumption is there is a clear distinction between independent and dependent variable, and goal is to model the relationship between independent and dependent variable. If I look at the interdependence analysis techniques, then the focus is to analyze the structure where the different kind of variables are interrelated and there is an underlying pattern with a data set without classifying the variables as dependent or independent. The goal is to understand the relationship and grouping within a set of variables, principal component analysis, factor analysis, cluster analysis, conjoint analysis, they typically fall into the domain of interdependence analysis techniques. All variables are treated equally and the focus is on identifying the underlying structure or grouping. Now, many times there is a confusion what to use when. So here you can find a summary of different kinds of tests and what is the condition under which they are widely used. So t-test, when you have to compare means of two groups, the assumption is normally distributed data. And suppose you want to compare the test score of two teaching methods, then t-test can be deployed. ANOVA, compare means of more than two groups. Normally distributed data, equal variances, compare test scores among three teaching methods. Chi-square test, it is also called goodness of fit test. Test independence between categorical variables, random sample, large enough sample size, and the example could be test if there is an association between gender and the preference for tea or coffee. Similarly, you have Pearson correlation that measures linear association between two continuous variables. Linearity and homoscedasticity are the assumptions and it examines the relationship between, let us say, examining the relationship between age and income. Regression analysis predict a continuous dependent variable based on one or more independent variable. The linearity, homoscedasticity, independence of errors are some of the adjacent. And suppose I want to predict the house price based on square feet or number of bedrooms, etc., then I can use the linear regression. Mann-Whitney, it is used to compare distributions of two independent groups. And it is based on the assumption that there is an independence of observations. Suppose I want to compare test score between two different schools. So both the schools are different, that their distribution is different. Kruskal-Wallis test compare distributions of more than two independent groups. Independence of the observation and similar distribution are the assumptions, and compare performance of different teaching methods across multiple schools will make a fit case for the Kruskal-Wallis test. Similarly, you have Wilcoxon-Sain rank test. Compare distributions of two related groups. Dependent variables should be continuous or ordinal, and compare pre-test and pre-test scores within a group could be a perfect example. Similarly, you can see that McNemar's test is for binary data, dependent groups, and Fisher's exact test is for low sample size, typically less than 20, and independence of the observation. Let us look at the hypothesis testing. What does it mean? And what are the important considerations and what is the procedure? So typically, hypothesis testing is a fundamental statistical method used to verify your assertions, make decisions, draw inferences about a population based on a sample data. It is a structured way to determine whether there is enough evidence, statistical evidence, to support a claim or hypothesis about a population parameter. You can see on the right hand side, the complete procedure is given. You state the hypothesis, declare your assertion, identify the test statistic, Just now we have seen what to use when and what is its probability distribution. Third, specify the significance level, at what level of significance you want to check your assertion. Number 4, state the decision rule about rejection or acceptance. Collect the data, perform the calculations, make the statistical decision, and make the economic or investment decisions. So what you see on the right hand side, let us say I have a null hypothesis. So I believe that this is true, mu is equal to mu 0, and alternate hypothesis is just reverse, mu is not equal to mu 0. So null hypothesis is about the status quo and alternate hypothesis breaks the status quo. So I have the normal distribution. I am defining my level of significance at 5%, which helps me to define my rejection area, which is in the hash region. And if, let us say, my point falls within this rejection region, then my null hypothesis is rejected. It means my alternate hypothesis is accepted. Let's look at the case study. Go Eats is a rapidly food delivery service operating in a mid-sized metropolitan area. The problem Go Eats experiences is about customer complaint regarding delivery times, particularly during the peak hours, lunch and dinner rushes. They suspected that current route optimization algorithm, which is primarily focused on minimizing distances, they are not able to effectively account for real-time traffic conditions and restaurant preparation times. So here my goal is to determine if new route optimization algorithm which can incorporate real-time traffic data and estimated restaurant preparation time can really significantly reduce the average delivery time or not. So my null hypothesis goes like this. There is no H0. There is no significant difference in the average delivery time between the current route optimization algorithm and the new algorithm. An alternate hypothesis says the new route optimization algorithm significantly reduces the average delivery time compared to the current algorithm. My methodology will involve collecting the data by implementing both the algorithms on delivery time, algorithm use, current or new, restaurant preparation time, estimated and actual, real-time traffic data, average speed on the route, distance travel, and the order time, and experimental design. I will choose to apply the random selection of the sample and random subset of deliveries typically were assigned to each algorithm. The sample size was chosen to ensure the statistical significance and deliveries were matched as closely as possible so that the two groups of deliveries had similar distributions of distances and order times. I am performing the statistical analysis using two sample t-test and setting the significance level 0.05. Analysis was performed to determine the impact of restaurant preparation time and estimation of accuracy, traffic prediction, and the implementation. If the t-test results indicated a statistically significant reduction in delivery time with a new algorithm, GoEats would implement it across their entire delivery fleet. So result would be two sample t-tests yielded a p-value of 0.001. The average delivery time for the current algorithm was 35 minutes, while the average delivery time for the new algorithm was 30 minutes. And the analysis of the restaurant preparation time and traffic data showed that the new algorithm improved the accuracy of both, resulting in better predictions. So typically, GoIt implemented the new route optimization algorithm, resulting in a 14% reduction in average delivery time during peak hours. Customer satisfaction is improved, complaints have gone down, and company also observed slight reduction in the fuel consumption because of the better routing around and traffic congestion policy. The study showed the importance of real-time data and restaurant preparation estimates into route optimization. So typically, when we say that I am checking my assertion or the hypothesis against a level of significance, then what is it and how to choose it? So typically, I have to consider a trade-off between type 1 and type 2 error because I am dealing with the probability distribution when I am testing the hypothesis and it is purely based on the random sample. So the distribution, what my sample is following is a probability distribution and hence I cannot be 100% sure in my decision making. I have to accept the risk of making a wrong decision under the given circumstances. So type 1 error occurs if the null hypothesis is rejected when it is in the fact true phase. So I'm rejecting the null hypothesis when it is true, and the probability of type 1 error is that is alpha is also called the level of significance. So that is the risk I am accepting. Type 2 error occurs if the null hypothesis is not rejected when it is fact false. So probability of type 2 error is denoted by beta, and unlike alpha, that is type 1 error, which is specified by the researcher, the magnitude of beta depends on the actual value of the population parameter, that is the proportion. So it is necessary to balance these two types of errors, and in balancing these, we have to select the appropriate level of significance. So this is the graphical representation of type 1 and type 2. On x-axis, I have the reality. On y-axis, I have the conclusions from the observed data, sample-based data. And suppose I am in the green region, right-hand side, upper corner, then I'm drawing the correct conclusion. I'm rejecting the H0 based on the sample data, observed data, and in reality, null hypothesis is false. So my decision goes absolutely right. Similarly, if I do not reject H0 and H0 is true in reality, I am also in the zone of green, which is the correct conclusion. But otherwise, left top corner, that is type 1 error, alpha, I am rejecting a true null hypothesis. It gives me the false positive conclusion. And similarly, I am inviting type 2 error, that is beta, the bottom of right. Do not reject a false null hypothesis and false negative conclusion is drawn. The example could be optimizing bus route system using hypothesis testing. I'm setting the null hypothesis. So typically a city's transportation system is considering to change the bus route 22. Currently route 22 runs a straight line from the city's east side to west side with stops every 500 meter, and department wants to test whether adding a loop to the route can really help to minimize the travel time. So adding the loop to bus 22 will not significantly increase the ridership is the null hypothesis. Alternate hypothesis, route 22 will significantly increase the ridership. I am collecting the data. Number one, current ridership data. So the department collects data on the average daily ridership of the current route 22 for a period of 30 days. So you must collect the data for a reasonably long duration of time. Let us say the average daily ridership mu0 is 500 passengers with the standard deviation of 50 passengers. Experimental route data, the department implements the modified route 22 with the loop for 30 days, and with this they are getting the average ridership, that is 560 passengers. I can deploy the statistical analysis and I can set the null hypothesis, alternate hypothesis. I can calculate the mean difference. So difference in mu1, mu0 is 560 minus 500. This is 60 passenger. The standard error I can calculate, that is sigma divided by square root of n. 50 divided by square root of 30 is 9.12. And I can calculate the z score, that is standard normal distribution score z, mu1 minus mu0 divided by SE, standard error, and this equals to 6.58. So now I can look at the calculated Z score with respect to my level of significance and see whether this falls into the rejection region or it falls into acceptance region. So I have chosen alpha is equal to 0.05. So Z score is 6.58, is far beyond the critical Z value, and hence it sets the premise for rejecting the null hypothesis. And based on this statistical analysis, there is sufficient evidence to conclude that adding the loop to bus route 22 can significantly increase the ridership. There are other factors we may consider to improve our decision making, like seasonal change could affect the ridership numbers, or other traffic related changes could also affect the ridership numbers. You can conduct the hypothesis testing using a very popular software, SPSS. I am giving you 3 links. Hypothesis testing, SPSS. The first one is of for 37 minutes. Similarly, SPSS hypothesis testing, one sample t-test, chi-square test in SPSS in interpretation. You can try hypothesis testing using these links in SPSS. Let us look at the another statistical technique, that is analysis of variance. It is also widely used technique when you have to compare more than 2 means, and typically the paired t comparison or t-test, paired t-test cannot really help you, as it increases the error in making the statistical inferences. So ANOVA, which is called analysis of variance, is a statistical technique to compare the means of 2 or more groups. Suppose I want to compare the lead time of vendor 1, 2, 3. So then I have more than 2 groups, and I can even the quality data coming from the vendor, number of defects for more than 5 batches, I can use ANOVA. So it analyzes the variance spread of the data to infer whether the means of different groups are significantly different. It breaks down the total variability in a data set into different components, allowing us to see how much of that variability is due to differences between the groups being compared. So this is a typical representation of ANOVA. On the left hand side, you can see that I am trying to compare the cells 1 and cells 2, and 2 normal distribution. What you see, I have the variation between group, means the mean of cells 1 is different than the mean of cells 2. And similarly, I have the variation within each group as it follows the normal distribution. The cells 1 has some variability. Similarly, cells 2 has some variability. So when I want to compare these two, yes, I can certainly deploy the t-test. But if I am comparing more than 2, it is always advisable to go for the ANOVA to reduce error in inference drawing. On the right side, you can see the blue, pink, and green, 3 different samples, distributions, maybe vendor 1, vendor 2, and vendor 3, and you want to compare the variations among the samples, because their mu1, mu2, and mu3 are different, and variation within the sample, that is, what is the variability within vendor 1, variability within vendor 2 data, and variability within vendor 3 data. You can see the statistical analysis table. So I am analyzing using ANOVA sources of variation within the sample, between the sample, and I consider the degree of freedom to calculate the mean squares, and based on the ratio of the mean square, MSB, mean square between your 2 samples or 3 samples, and mean square within, that is the variability within the sample, I can find the F statistic, and this F statistic, I can compare the value for the given level of significance in the standardized statistical table and make the appropriate decision about the acceptance or rejection of the null hypothesis. We can look at the case study. NFL, National Freight Lines, is a trucking company focused on optimizing fuel efficiency and identified basically the tire rolling resistance as a significant factor contributing towards fuel consumption, and they are testing the 3 different kinds of brands A, B, and C of the tires, and they want to check statistically what is the difference in terms of the efficiency, that is kilometer per liter each particular tire is offering. So they have 6 truck. It's a hypothetical data to illustrate the concept of ANOVA. You have tire brand and it is giving me 4.8 kilometer per liter, 4.9, 4.7, and so on. You have tire B, which is giving me 5.2, 5.1, 5.3, and so on. And you have tire C brand, which is giving me 5.8, 5.9, 6, and so on. I am deploying the hypothesis that there is no significant difference whether I use tire A, tire B, or tire C. An alternate hypothesis is about breaking the status quo. Yes, there is a difference in terms of the mean fuel efficiency. I am calculating mean and variance for each tire brand, then calculate the overall mean, typically your X double bar, calculate the sum of square SSB, sum of square within SSW, calculate the mean square between MSB by dividing with the degree of freedom, and M square within again by dividing SSW by degree of freedom, and calculate the F statistic. All these things you can tabulate in the ANOVA table as I have shown previously, and then you can make the decision considering your level of significance or the p-value, where your calculated p-value or the f value with respect to your level of significance or your critical value, which is derived from your statistical table, falls. And if it falls within the rejection region, for example, alpha is equal to 0.05, then you reject null hypothesis. It means there is a significant difference in the tire brand so far the mean fuel efficiency is concerned. So this is what the interpretation is, and based on ANOVA results, NFLKL makes sound informed decisions that which tire brand they should use to maximize the fuel efficiency and reduce cost. You can use these videos, one-way ANOVA, post-hoc test using SPSS, conducting a two-way ANOVA to effectively utilize SPSS, and even for a larger data set, conduct your analysis using a quite user-friendly software like SPSS. Let us see the third important technique, that is regression analysis. Regression analysis is a statistical process for estimating the relationship between a dependent variable, that is the outcome or the response, and one or more independent variable, that is the predictor or covariates or explanatory variable or features. For example, I want to identify the price of a product, and this is the dependent variable, and on the other side the independent variable could be the features, the market dynamics in terms of number of customers or the customer preferences, and the various customer product specifications which influences the price. I can consider and determine the pricing of the product. So let us look at the case. And urban traffic congestion is a major concern across all the metro cities across the world, and typically it impacts the commute time, fuel consumption, and most importantly AQI, your air quality index. So understanding the factors influencing traffic flow is crucial for effective management of the traffic, and this study intends to investigate the relationship between traffic volume, vehicle per hour's average speed on a selected urban setting, your arterial road, using the regression and correlation analysis. So I'm collecting the data, specific arterial road segment during peak hours 7 a.m. to 9 a.m. over 10 weekdays, and I have the data points as recorded for day 1 to day 10, traffic volume, average speed. So 1200, 1500, 1800 is the traffic volume, and average speed is 45, 40, 35, and so on. I can calculate the correlation. I can conduct the correlation analysis. So I have calculated the X bar, sigma X divided by N, and sigma Y divided by N, that is Y bar, and calculate the standard deviation Sx and Sy I can calculate the covariance, which comes out to be minus 1594.44, and I can calculate the correlation coefficient R, which is minus 0.98. So it indicates that these two are strongly but negatively correlated. So the correlation efficient R is minus 0.9, indicating a strong negative linear relationship between traffic volume and the average speed. And as traffic volume increases, the average speed significantly goes down. So I can further conduct the regression analysis, y is equal to a plus bx, and I can compute the coefficient like b, which is covariance xy divided by sx square, which comes out to be minus 0.0187. A is equal to y bar minus bx bar, which comes out to be 67.885. So my regression equation, y is equal to 67.885 minus 0.01875x. And I can very easily calculate the slope, that is minus 0.0187, every additional vehicle per hour, and intercept is 67.885. So I can calculate the coefficient of determination, which basically explains the variability within the which is explained by my independent variable in the regression model, and R square comes out to be 0.96. So 96% of the variation is explained through the average speed for the traffic volume, which is quite good. And residual analysis, I can plot the residuals, that is the difference between predicted value, observed value, and the predicted value. And I can look into the trend of residual analysis for linearity, constant variance, and normality, which are some of the assumptions to be satisfied as a part of regression analysis. So the practical implications, the strong negative correlation highlights significant impact of traffic volume and average speed. It can be used to predict average speed for different traffic volume scenarios, and I can provide that signal to my users so that at one side traffic can be managed through the speed, and also the congestion and the pollution can be controlled. So this case study demonstrates the application of regression analysis and the kind of important policy decisions can be drawn using such kind of predictions. Broadly, you can classify the regression models into linear regression, multiple regressions, non-linear regression, or if I expand it further, then types of regression models. On the right-hand side, you see is the linear regression, logistic regression, polynomial regression, stepwise regression, ridge regression, lasso regression, elastic net regression. So your linear regression perfectly sets a linear trend or line between your x and y, dependent variable and independent variable. Polynomial regression is your non-linear regression, similarly the logistic regression. If we quickly look at the different kind of regression models, then linear regression explains the linear relationship between dependent and independent variable, maybe predicting transport cost based on distance, weight, and fuel price. Could be a fit case for linear regression, forecasting demand based on historical sales data and marketing spending. On the other hand, you have logistic regression. It is used when you want to have dependent variable which is binary in nature, yes or no, 0 or 1. It predicts the probability of an event occurring. And for example, you want to predict the probability of a shipment being delayed. Determining the likelihood of customer accepting a delivery offer or assessing the risk of a supplier falling to meet delivery deadlines fits within the scope of logistic regression. Polynomial regression, it is non-linear relationship by fitting polynomial curve to the data. It is specifically useful when the relationship between variables is curved rather than the linear. And a couple of examples could be analyzing the relationship between inventory levels and storage cost, which may not be linear, modeling the impact of temperature variation on product degradation over time, typically your cold chain, optimizing delivery routes where time versus distance may have polynomial relationship. If we look at the ridge and lasso regression, then these are regularization techniques which are used to address multi-collinearity. That is the high correlation between independent variables. Some of the independent variables, they have very high correlation, and because of this high correlation, this correlation itself generates an impact on your dependent variable. So they help overfitting the model and improve the stability of the model. So ridge regression shrinks the coefficient, and lasso regression shrinks the coefficient and can perform variable selection by shrinking some coefficient even to zero. So a couple of examples: managing inventory within numerous related factors like sales of similar products, analyzing supplier performance with many potential correlated metrics, and forecasting demand from many promotional activities that may be correlated. When you use the regression model, three dimensions are very important. Number one, data quality. So accurate and relevant data are absolutely a necessity for reliable regression model. Model selection, as I indicated, the different types of regression model, it depends upon the nature of data and research question. And number three, model evaluation. So just fitting a regression model is not enough. How good your model is, you can apply the different kind of test. You can check for R square, you can check for adjusted R square, you can check for the line assumptions of linear regression, that is the linearity, equal distribution, and using the typically your residual, you can conduct the test for the various line assumptions of the regression model. So typically when we talk about the epsilon error, it is the difference between the observed value and the predicted value. And this epsilon has a very, very important role in performing the residual analysis, typically to judge the goodness of fit of my regression model. So on the right hand side, you can see that when I'm putting my residual, that is the predicted versus actual values for the revenue, for example, then they are fitting my normal probability plot, all are falling within one line, and I can say that my linearity assumption is satisfied. Similarly, I want to check the randomness in the error. So residue, standardized residual versus predicted value for the revenue, I can see it is quite scattered, not fitting on the normal probability plot in one line, and my line assumptions or linearity normality assumptions are violated. Let us see the example. The context is metro rail authorities want to understand how station connectivity measured by the number of interchanges with other lines, bus terminals and railway stations impact the daily ridership, because you have to reach to the metro, and for that you need the convenience of maybe the bus terminals or the railway stations and so on. So data we have presented here, that is the hypothetical one, and you can collect the data from a sample of metro stations over a period of time. So S1 to S10 are stations, number of interchanges are 1, 0, 2, 1 and so on, and the third column indicates the average daily ridership: 15,000, 8,000, 25,000, 18,000, 35,000 and so on. I can use the correlation analysis to find the value of correlation coefficient, typically Pearson correlation coefficient R equal to sigma xi minus x bar into yi minus y bar divided by square root of sigma xi minus x bar square into sigma yi minus y hat square. So regression analysis I can conduct by using this data y is equal to a plus bx. I can determine, as shown previously, the coefficient value of a, coefficient value of b, and let us say I can come out with the regression y is equal to 5,000 plus 10,000 x. Then if a station has 4 interchange, the predicted ridership would be 45,000 passengers. This can really help the station manager authority to plan for the various options to handle this flow of passenger on a given time. So you want to predict the daily ridership. connectivity, number of interchange. There are various optimization applications. You can do route planning. This regression model can help to identify the optimal location for new metro stations and interchanges. You can do station development. It is all about the capacity, improving connectivity. Feeder services based on the predicted ridership at station with high connectivity. Metro authorities or manager can optimize feeder bus routes, capacity planning. So metro can plan for appropriate train frequency, car numbers, real estate development, and so on. So once again to mention data accuracy, the other factors like factors that influence the ridership may be your pricing or other strategy, population density, land use matters, time of day matters, geographical factors, population density, availability of alternate transport, and external events such as festivals, sporting events, they have the direct impact on your regression model. So it's important to appreciate that correlation is the relationship between two variables, and regression is how well a certain independent variable predict the dependent variable. Correlation is not causation. Causation is about investigating the cause and effect relationship. Correlation is about investigating the strength of relationship between two variables. So you can see these scattered diagrams. The first one on the left side is positive correlation. The next one is the negative correlation. And in the third one, you see that all the data is scattered and absolutely there is no correlation. There are important assumptions which must be satisfied if you want to accept your regression model. One is linearity. There has to be linear relationship between independent and dependent variable. Independence, observations are independent of each other. In other words, the value of one observation does not influence the value of other. Third is homoscedasticity, which is the assumption that states that variance of errors, that is residuals, is constant across all levels of independent variables. And if the variance of errors is not constant, it is called homoscedasticity, which can lead to unreliable results. The fourth is normality. My errors residuals are normally distributed, and this assumption is primarily important for hypothesis testing and constructing confidence interval. No multicollinearity. This assumption means that independent variables are not highly correlated and their significant correlation does not have the capability to influence my dependent variable. So this assumptions really matters. Otherwise, you are accepting the regression model, which is really not fit for the use. And we can check the assumptions using residual plots, correlation matrices, or different kind of statistical tests like Durbin-Watson test for independence or Shapiro-Wilk test for normality and others. Residual analysis is very important analysis. In regression analysis, or once you have developed the regression model, it basically acts as a diagnostic tool to judge the quality of the regression model. So residual is the difference between observed value and the predicted value. And typically, the residual analysis is used for model validation, whether my regression model is appropriate for the data or not. So assumption checking, regression model rely on certain assumptions like linearity, normality of the residuals, and constant variance. And typically, I may identify the problems like non-linearity in the data when I do the residual analysis, unequal variance, that is called heteroscedasticity, outliers that significantly influence the model, non-normally distributed errors, and dependent errors. All these I can do using the residual analysis. So typically I can use the different kind of representation, graphs, residual versus fitted value to check for non-linearity or homoscedasticity. normal QQ plot to check for the normality of the residuals, and residuals versus predictor variable to check for patterns related to specific predictors. I can also look into the patterns and try to interpret. So a random scatter of residual increase is a good fit. Patterns like curves or funnels suggest violation of the assumption. There are various goodness of fit tests really to check whether my regression model is fit for the use for the given data or not. So one of them is R squared coefficient of determination that explains the proportion of variance in the dependent variable that is predicted from the independent variable. Ranges from 0 to 1, and 1 indicates the perfect fit. So if you have 90%, 95% R square value, it is much appreciable. Use cases widely used in linear regression, and it provides a general sense how well the model explains the data. There are certain limitations. R squared can increase simply by adding more independent variables, and this may result into the overfitting of the model. So there we make use of adjusted R square, is the modified version of R square, and it penalizes the inclusion of unnecessary variables and hence the overfitting of the model. So it modulates the value of R square, and hence R square and adjusted R square should be used as the complementary measures. Root mean square error. RMSE measures the average magnitude of error in the model's prediction and commonly used to evaluate the accuracy of the prediction. Similarly, we have mean absolute error, average absolute difference between the predicted and the actual values, and it provides a measure of the average magnitude of error, similarly like RMSE. You can use the app statistic to evaluate the overall fit of the model. You can use AIC, that is Akaike information criteria, and Bayesian information criteria, BIC. Typically, AIC and BIC are information criteria used for model selection, and they balance the goodness of fit with the complexity of the model. So they are useful for comparing different regression models and selecting the best one. So already I mentioned you can have logistic regression, or you can have linear regression, non-linear regression, polynomial regression. You can choose the best one for the given situation. So the key considerations are goodness of fit indices depends on specific goals of the analysis, and it is very important to analyze your regression model, doing residual analysis and finding the various goodness of fit indices to see that your indices fall within the permissible acceptable range or not, and hence your model, regression model, is fit for the use of class of data you are considering. You can conduct the regression analysis using SPSS. So two video links you can see here for conducting correlation and regression or Pearson correlation analysis as a part of broadly your regression analysis. The third important, or rather fourth important technique is the structural equation modeling. And structural equation modeling is a multivariate analysis technique which combines the factor analysis and path analysis. Multiple regressions you conduct to evaluate the complex relationships between observed and latent variables, often used to examine the causal relationships. So SCM is a statistical framework. Researchers use this framework extensively across all the domains, and they include both observed, manifest, as well as unobserved latent constructs. So for example, latent variables are those constructs or concepts that are measured indirectly through multiple indicators. So for example, customer satisfaction, I can measure it through different their purchase behavior or repeat orders. I can measure it through some observed variables. Measurement model is a part of SCM, which describes the relationship between latent variables and their indicators. So customer satisfaction is the latent variable, and maybe the repeat order or their behavior pattern or loyalty, they all are the indicators. Structural model, this part specifies the causal relationship between the latent variables themselves. Now you have one latent variable, customer satisfaction. Similarly, you have many other latent variables, and you can put these latent variables together to understand the structural relationship among them. That is where structural model is prescribed. Path analysis is used to visually represent and analyze the relationship between variables in the structural equation modeling. So how it works? You have model specifications, you formulate a theoretical model based on your literature review, interaction with the world, outlining the relationship between variables. You collect the data to test the model, model estimation, statistical software you can use to estimate the parameters, path coefficient, whether the relationship is significant or not. Then model evaluation, fit of the model to data is assessed using various statistical indices, and model modification. If the model does not fit well, then you have to modify the model because your initial assumption about the relationship between variable is not appropriate, and then you re-estimate it. So SCM is widely used in social science. You may like to study the relationship between constructs like attitudes, behavior, outcomes, psychology, structure of personality traits, mental health constructs, businesses, relationship between marketing strategies, customer satisfaction and sales, and so on. There are numerous advantages because it analyzes the complex relationships, patterns, multifaceted theories, and can handle both observed and latent variables simultaneously. There are some limitations because the number of variables and complexity involved is higher. It requires a large sample size, can be complex to interpret and implement, and assume linear relationship between variables. So let us look at the example, the case study, optimizing supply chain resilience through digitization and collaboration. So in today's dynamic logistics supply chain, resilience is important. How my supply chain and logistics can bounce back under the condition of disruption, maybe natural disaster or calamity or any other thing. And this is where I want to consider the economic fluctuation, natural disaster, geopolitical event as a part of my model and understand the intricate behavior among these variables. So research question, how do digitization and collaborative relationship influence supply chain resilience in the logistics sector? My hypothesized model, digitization is having the relationship with the collaborative relationship. Digitization is having impact on supply chain resilience. Collaborative relationship and supply chain resilience are also correlated. So I can provide the coding. So DIG1, that is latent construct of digitization, adoption of real-time tracking system. You can put it on the scale of 1 to 5. 1 is not at all adopted. 5 is the extensively adopted. DIG2, implementation of cloud-based inventory management. DIG3, use of predictive analytics for demand forecasting. Then collaborative relationship, latent variables could be COL1, information sharing with supplier and customer. COL2, joint problem solving with partners, long-term strategic partnerships is COL3. Similarly, you can define supply chain resiliency, latent variables, RSC1, ability to recover from disruption quickly, RSC2, flexibility to adapt to changing conditions, RSC3, robustness of supply chain operations. I am putting the statistical data collected based on large-scale survey. Then I am deploying the SCM model. The first I am developing the measurement model. So first assess the measurement model to ensure that the observed variables adequately represent the latent construct. It should not happen that the latent construct really are not appropriately explained by the observed variable. So this part needs to be checked. For example, if factor loading of DIG1, digitization 1 latent factor is low, it means that this variable does not accurately represent the digitization latent variable, and I may have to modify my measurement model. Structural model, once the measurement model is validated and you are okay with it, it means your latent variables are appropriately explained by the observed variable. Then the researcher would estimate the structural model to test the hypothesized relationships. So then you do the model evaluation using various goodness of fit indices, CFI, TLI, RMSEA, SRMR. We will see this. Interpretation based on the path coefficient, you can determine the extent to which digitization and collaborative relationship influence the supply chain resilience. And this can help you to take appropriate policy measure and investment related decisions. There can be various political implications. Logistical companies can use the findings to prioritize investment into the digitization and foster stronger relationship with the partners. Empirical evidence can be drawn for the importance of this factor in enhancing the supply chain resilience. All these are practical implications, and the company can use the data to create specific strategies that increase their resilience. You can use R, M plus or MOs to conduct the structural equation modeling analysis. So broadly, it goes like this. I have a theoretical model drawn based on the literature review, the real life interactions. I am putting it in the form of causal relationship diagram. I am developing and testing the structural and measurement model, then estimating and evaluating, then calculation of eligibility criteria, and finally, there is an interpretation of the results. So if you look at on the right hand side, then latent and observed variable I have, endogenous and extraneous variables. Endogenous variables is the dependent variable and extraneous variables are the independent variables. Then I have exploratory and confirmatory factor analysis. So I will use the exploratory factor analysis to determine the extent and nature of linkages. They are not predefined. But in case of confirmatory, I already have the relationship predefined and I want to confirm. Measurement and residual error. So errors in the measurement of the value of latent variable from the observed variable is defined as measurement error. And residual error is the error in predicting the value of endogenous variable from the exogenous variable. Then I come to the measurement and structural model. Measurement model represent linkage between latent and observed variable, and structure model explains the relationship between the latent variable. My path diagram finally is the visual representation of the model prepared to state the linkages between the observed and the latent variable. So it goes like this. I have the theory. I construct the model, instrument construction for data collection. I collect the data, model testing, and final interpretation of the results. So these are some of the, let's say, notations used in structural equation modeling. Type of indicator, you have exogenous, endogenous, X and Y, notation X number, Y number, X1, Y1. Type of relationship, maybe measurement loading, structural path coefficient, correlation between constructs, COV, error terms, indicators, and constructs. So SEM depends on two most important things. One is the measurement model, another is the structural model. Measurement model, as I mentioned, defines the relationship between observed variable and latent variable, and latent variable are unobservable constructs. For example, customer satisfaction is the latent variable. Maybe you can conduct the survey. How satisfied are you with the product's quality, customer service? How likely are you to recommend this product? And this can help you to understand the latent variable, that is the customer satisfaction. Similarly, you have the structural model, which defines the relationship between latent variables themselves, and it tries to dig out what kind of interconnections they have in order to have their influence on the phenomena which is being investigated. So maybe you are trying to deal with the customer satisfaction, and product quality is the latent variable which can positively influence the customer satisfaction. Another latent variable, you have customer satisfaction, which is the latent variable, which can again have an impact on the customer loyalty, could also be the latent variable. So this is the typical representation of the measurement model, where let us say you have the supervision at one side, you have the co-workers, you are trying to figure out the covariance between supervision and co-workers. Each particular, say, latent variable is defined, supervision, which is a latent variable defined by x1, x2, x3, x4, which are the observed variables, and each has the error component ex1, ex2, ex3, ex4, and similarly for the co-workers. You can define the structural model like this, which I mentioned. It defines the relationship among the latent variables like supervision, work environment, co-workers, job satisfaction, and job search. All these are interrelated, and it tries to investigate the relationship among these important latent variables. So this is the another example where supervision, environment, co-workers, and you are now trying to put it in the form of hypothesis. I'm trying to investigate H1, whether supervision and job satisfaction, they are positively or negatively related. When I'm considering the relationship among the various latent variables, supervision, work environment, and co-workers. Similarly, H2, the impact of work environment and job satisfaction, co-worker and job satisfaction, and job search, that is H4. These are the various stages well prescribed in the well-known reference here, et al. 2014. You begin with the stage 1, define the individual constructs. Stage 2, develop and specify the measurement model. Stage 3, design a study to produce empirical results. Stage 4, assess the measurement model validity. If the measurement model is valid, as we discussed, yes, proceed to test the structural model. If not, then refine the measurement model and design a new one. If it is valid, I will go to stage 5, specify the structural model. Stage 6, you assess the structural model validity using goodness of fit indices. And if the structural model is valid, then draw the substantive conclusions and recommendations. If not, refine the model and test with the new data. So these are the steps described. Define the constructs, develop and specify the measurement model. Step 3, you design a study to produce the empirical result, assess the validity of the measurement model, specify structural model, and finally check the validity of the structural model using the goodness of fit indices. The most important question in structural equation modeling is what should be the sample size. There is a very clear-cut guidelines on the selection of the sample size. The recommendation 1, if there are 5 or fewer constructs in your model, each with more than 3 items, that is observed variable, your x1, x2, x3, and with high item communalities, 0.6 or higher, recommended sample size is 100 to 150. Recommendation 2, modest communalities, 0.45 to 0.55, or the model contains construct with fewer than 3 items, you go for 200 sample size. Recommendation 3, lower communalities with multiple under-identified fewer than 3 items construct, you have to go for higher sample size to improve the discriminatory power of your analysis. Recommendation 4, more than 6 factors with select factors using less than 3 measured items as indicators. Presence of multiple low communalities, you have to really go for very, very large sample, that is more than 500. Most important part to check your structural model, and that is where you have to make use of different goodness of fit indices. Broadly, they are classified into absolute fit indices, incremental fit indices, and parsimony fit indices. If you look at the absolute fit indices, then model chi-square is one of the fit indices. So it is used for sample n is less than or equal to 200 or p is greater than 0.05. Insignificant result if it is p is greater than 0.05. So here the range or the threshold limit cutoff value is indicated. Similarly, chi-square divided by degree of freedom, the value should be less than 2. RMSEA, the value should be between 0.08 to 1. GFI, goodness of fit statistics, value should be greater than 0.9 or greater than 0.95. AGFI, adjusted goodness of fit statistics, value should be greater than 0.8. So whatever package R or SPSS or ANOVA you are using would help you to calculate these indices, and based on the cutoff value, you can judge the quality of your structural model. Your incremental fit indices like NFI, normal fit index, non-form fit index, CFI, comparative fit index, and everywhere the cutoff value is prescribed. So typically this is what we discussed: your absolute fit indices, incremental fit indices, and parsimony fit indices. Typically, parsimony fit indices adjust for model complexity, favoring simpler model. So these considerations are very important when you deploy the fit indices, GFI, goodness of fit indices for SCM. Cutoff value for goodness of fit can vary depending on the field of study, complexity of the model, slight variations you can accommodate, and researchers should prioritize theoretically sound models over those that simply have the best statistical fit. This is the example where social marketing online climate change is linked with perceived ethical capability and behavioral intention, and there are various indicators for trust, commitment are specified. So this is the example in the domain of multimodal transport network. A city has implemented multimodal transport network that integrates buses, trains, bike sharing, and the research quotient they want to investigate using the structural equation modeling. How do system efficiency and perceived accessibility influence user satisfaction in multimodal transportation system? So system efficiency is linked with perceived accessibility, system efficiency is linked with user satisfaction, and perceived accessibility is linked with user satisfaction. You want to investigate the relationship among these latent variables. So you can define your latent variables: EFF1, average travel time; EFF2, system efficiency latent variable, on-time arrival rate. Similarly, ACC1 to ACC3, perceived accessibility, user satisfaction, SAT1, SAT2, SAT3. You can collect the data, you can create the measurement model, check the validity of the measurement model, go for the structural model. And if the structural model is valid based on the goodness of fit indices, which are CFI, TLI, RMSEA, SRMR, and others, then you draw the appropriate interpretation. The expected outcomes of the structural equation model could be: system efficiency will positively influence perceived accessibility and user satisfaction. Perceived accessibility will positively influence user satisfaction, and this analysis will provide quantitative insight, the foundation into the effectiveness of multimodal transportation system. You can conduct SCM using SPSS. Two video links are provided here, AMOS, and this can help you to calculate all the various goodness of fit indices, model validity, and construct your model and validate it. The another important technique in statistical analysis is principal component analysis. We can look at the context. Let us say large logistic company operating a diverse fleet of trucks across a vast geographical region faces challenges in optimizing its fleet management. They collect the weather data, including a wealth of data correcting fuel consumption, vehicle maintenance record, driver performance, route information, delivery times, vehicle age. The problem is analyze the high dimensional data set to extract meaningful insights is difficult. identifying the most influential factors affecting the fuel efficiency and maintenance cost is crucial for cost reduction. And typically, the company wants to improve the predictive maintenance and optimize routing. So, the solution is to deploy principal component analysis. You can process the raw data, handle missing values. PCA can be implemented to standardize the data set to reduce the dimensionality. Analysis and interpretation, the first few principal components which capture the majority of variance are analyzed. And suppose, let us say, PC1 is found, which primarily represent the factor related to vehicle utilization, route efficiency, distance traveled, or traffic condition. PC2 can reflect vehicle maintenance and driver performance. PC3 can reflect vehicle age and fuel consumption. And then you can apply your analysis and results for predictive maintenance, route optimization, driver training, fleet renewal, and performance monitoring. The benefits could be fuel consumption reduction, maintenance cost reduction, enhanced driver performance, optimized routing and delivery times, and so on. So typically, PCA is a powerful statistical technique used for dimensionality reduction because I cannot deal with so many variables and really create a sound policy. So it essentially transforms a large set of variables into a smaller set of principal component which has significant impact on the phenomena which is being investigated or under consideration. So PCA identifies the patterns in the data, finding the direction that causes most variance, and it projects the data into this new direction, reducing the number of variables. So it is important because it offers the dimensionality reduction, data visualization. PCA can reduce the data to 2 to 3 dimensions. Noise reduction. So by focusing on PCA that captures the most variance, PCA can filter out the noise and redundant information. Feature extraction can create new and meaningful features from the original data that can help to create new insights from the data. So a couple of examples, we may even see image compression. Image can be represented as a large number of pixels, and PCA can reduce the number of pixels needed to represent image, reducing file size. Genetics, it can be used to identify patterns in the genes, expression data, helping researchers to understand how genes are related to disease. Finance, PCA can be used in the stock market data, identifying the factors that drive the stock prices, and similarly, customer segmentation, PCA can be applied. Supplier performance evaluation is one of the domain where you have the various matrices like on-time delivery, defect rate, cost, lead time, responsiveness. PCA can help you to reduce all these factors into two. PC1 may represent reliability, PC2 might represent the cost effectiveness. And this simplified supplier evaluation can allow for better comparison among the potential suppliers. Similarly, demand forecasting, which depends on marketing spend, seasonality, economic indicator, competitor actions, you can define this entire complex domain using PCA into two PCs. PC1 might represent overall market trend, PC2 might represent seasonal effect. Similarly, inventory optimization, transportation and route optimization, PCA has significant impact in decision making. So one example, if we see then regional transport authority needs to prioritize road infrastructure project due to limited budget, and they have collected data maybe on various road segment, traffic volume, vehicles per day, payment conditions, index PCI, a measure of payment quality, 0 to 100 is the higher is the better, accident rate, accident per kilometer per year, population served, economic impact, estimated increase in the regional GDP due to road improvement. And you can see that for the road segment A, B, C, D, E, traffic volume 15,000, 8,000 and so on, the PCI, that is your payment condition index, accident rate, population served, and economic impact, the data is gathered. I can standardize, follow the steps of PCA analysis, calculate mean and standard deviation. Then I can calculate the covariance matrix of the standardized data. Then I can calculate the eigenvalues and vectors of the covariance matrix. I can select the principal component, sort the eigenvalue in descending order, calculate the proportion of variance explained by each principal component, determine the number of principal component, typically those who have significant proportion of the variance, say 90% or more than 90%, in data transformation, transform the original data into new coordinate system defined by the selected principal components. So this is just an example, and you can very well see the eigenvalues. PC1 is 3.2, PC2 is 1.1, PC3 is 0.4, PC4 is 0.2, PC5 is 0.1, and the explained variance by PC1 is 64%, PC2 is 22%, PC3 is 8%, PC4 is 4%, PC5 is 2%. The cumulative variance you can see. So broadly, we can see that PC1 and PC2 are most impactful so far. The variance is explained, which is 64% and 22%. So PC1, high positive loading for traffic volume, population served, and economic impact, and moderate negative loading for accident rate. PC2 has high positive loading for PCI, payment condition index, and moderate positive loading for the economic impact. You can interpret that PC1 represents combination of factors which are related to the overall importance and usage of the road segment, traffic population, economic impact. PC2 primarily reflects the payment condition to some degree of economic impact. So broadly, the steps involved in principal component analysis is the standardized range of continuous variables, compute the covariance matrix, then compute the eigenvectors and eigenvalues of the covariance matrix to identify the principal components, create a feature vector to decide the principal components, and recast the data along the principal component axis. You can conduct the principal component analysis using SPSS. You can consider these two links to understand how PCA can be conducted using SPSS. The another important technique is factor analysis. So typically it is a statistical method to describe variability among observed correlated variables in terms of potentially lower number of unobserved variables called factors. So I have many factors to deal with, and suppose I want to condense this list and identify the representative factors which basically indicates or represents set of factors, then this dimensionality reduction technique, factor analysis, is highly useful. So it is a dimensional reductionality techniques like PCA reduces the complexity of data, considering large number of variables into smaller set of factors. But unlike PCA, which focuses on explaining variance, factor analysis seeks to identify latent, which are unobserved variables that explain the correlations between observed variables. So these latent variables or factors represent underlying concepts or construct, and typically it is about understanding the relationship. Factor analysis help understanding the relationship between variables by revealing which variables are strongly associated with each factor. So it provides the data simplification, construct validation is important, scale development matters, and identifying underlying patterns is the object. So there are various examples where factor analysis is successfully used. Market research, I want to analyze the customer survey data to identify the underlying factors that influence purchasing decisions. Factor analysis may reveal factors such as product quality, price sensitivity, broad loyalty, representing many other factors or variables. Similarly, human resource, communication skills, teamwork, problem-solving capacities, or abilities can be extracted at some of the important factors: customer segmentation, brand perception, risk assessment, operational efficiency, variety of applications where factor analysis is highly useful. We can look at the quick examples. Understanding the user perception of e-scooter service in urban environment. And company surveyed 500 e-scooter users, asking them to rate their experience on a scale of 1 to 7 on safety, convenience, affordability, reliability, maintenance, ease of use, environmental impact, and parking availability. So I have gathered the data from 500 users on this 8 dimensions. I'm analyzing it using the factor analysis and reduce the number of variables to identify underlying dimensions of user perception. I will find the correlation matrix, factor extraction, factor rotation. Typically, Variance rotation was applied to make the factors more interpretable, and rotation helped to clarify the relationship between variables and factors. Factor interpretation, maybe I can extract at the end of the analysis. Factor 1, operational efficiency, loaded heavily on safety, reliability, maintenance, ease of use, and parking availability. And factor 2, accessibility and value, which basically describes or loaded heavily on convenience, affordability, and environmental impact. So I can use these results to reduce the 8 variables into 2 factors, which is one of the important benefit: operational efficiency, accessibility, and value. And company learned that users primarily evaluate the e-scooter service based on its operational aspect, safety, reliability, inaccessibility, and value, rather than getting lost into 8 different factors. I can focus now on these 2 factors in the design of e-scooters and services. So the steps involved are like this: formulate the research question, gather the data, check for sampling adequacy, choose the factor extraction method, determine the number of factors, rotate the factors, and interpret the results. The another example which we just talked about can be considered for factor interpretation, and I can analyze the public transit user satisfaction using the factor analysis, and that can help me to understand that if there are 8 factors involved, what are those 2 important factors or 3 important factors like service quality, user experience, and potentiality cost, which overall describes the underlying phenomenon. So there are important assumptions in the factor analysis which is to be satisfied. Measure variable are linearly related to the factors. Errors. These assumptions is likely to be violated if the items limited response scale, 2-point response scale like true, false, right, wrong items. Data should have a bivariate normal distribution, jointly normal for each pair of variable. Observations are independent, and factor analysis model assumes that variables are determined by common factors and unique factors. All unique factors are assumed to be uncorrelated. You can conduct the factor analysis using SPSS. These 2 links will help you to understand how SPSS can be used to conduct factor analysis. The another important method is the correspondence analysis. It's a multivariate technique which basically relates the different, it sets the correspondence among different items or entities, and it deals with the categorical data and provides the perceptual map. So basically, it helps us to visualize the relationship among the different kinds of variables in a 2D way. It analyzes the categorical data where variables are qualitative rather than quantitative. And it is important because it's powerful ability for exploring categorical data, market segmentation, brand positioning, customer behavior analysis, product development, and so on. So a couple of examples we can see that product preference, your CA, correspondence analysis can help to establish or understand the relationship between customer demographics, that is age, gender, income, and product categories, clothing, electronics, groceries, brand association. It can analyze survey data on consumer perception of different brands, your brand A, brand B, brand C, and innovative, reliable, and affordable brand attributes. Similarly, media consumption and customer satisfaction. It provides correspondence analysis a valuable tool for understanding and visualizing relationship between categorical variables, leading to better insight and more informed decision. So you have the inputs in the form of categorical variable, contingency table of frequency data, activities capture measures of association, compute fit measures, creates perceptual maps, and output would be perceptual map, different fit measures, numerical measures for interpretations of the CA results. So we can just quickly look at the example that case study analyzing customer preference for delivery options, and there is a e-commerce logistics company, SwiftShip, and it wants to analyze and understand how customer demographics relate to their preference for different delivery options. Customer age group is 18-25, 26-35, 36-45, and 46 plus. Preferred delivery options is standard, express, scheduled, click and collect, and so on. I have gathered the data for the demography, that is the age group, standard, express, scheduled, click and collect, and I can deploy the correspondence analysis. Data input contingency table is used as an input. Chi-square distance calculation is performed to understand the distance among the different set of factors. Singular value decomposition, SVD, is performed to decompose the chi-square distance matrix, reducing the data to lower dimensional space, two-dimensional for easy visualization, and I can create the perceptual map. Maybe points representing age groups are plotted based on the row profiles. Points representing delivery options are plotted based on the column profiles. The closer two points are, the stronger are the associations. So I can have the different kind of outcomes. Maybe for instance, 18 to 25 age group is close to click and collect. Maybe 46 plus is close to scheduled. 26 to 35 is close to the delivery option express. 36 to 45 is close to the delivery option, maybe standard. This can help my business to formulate the better business delivery strategy. So there are various practical implications in terms of targeting the market, service optimization, inventory management, improved customer satisfaction when this SwiftShip company, they deploy the correspondence analysis. The another example could be the public transport, where you want to check the employment sector, healthcare, education, technology, retail, and could maybe you want to relate it with the preferred mode of transport, bus, train, subway, bicycle, and walking. Similarly, I can conduct the analysis using correspondence analysis, data input, chi-square distance calculation, SVD, perceptual map, and then interpretation that whether my healthcare and subway is close to the other dimension, bicycling or walking, or maybe it is more close to subway or education and train. If education and train are close, then what kind of information or policy I can draw. So this can have various implications for the authorities, service optimization, infrastructure planning, targeted communication, resource allocation, and so on. This is the perceptual map sample where I'm relating the vendors with the different defects. I can very well see that vendor 1 is broadly having the plating defect. Vendor 2 is having hole missing defect and plating defect. Vendor 3 is more close to plating defect and debarring defect. Vendor 4 is more close to fasten in installation. Now, depending upon the severity of the defect, I can decide the contract conditions, penalties with each vendor, or I can decide the evaluation criteria for the selection of the vendor. So you can use these two links to perform your correspondence analysis using SPSS. The most important widely used technique, which is an addition to this bucket of statistical technique, is cluster analysis. So it's a data mining technique which groups these similar data points together into clusters, I want to discover the hidden patterns. I want to segmentize the data, maybe customer-wise, age-wise, or I want to simplify the complex data, and cluster analysis is highly useful. So you can just look at when I do the grouping or clustering, then my objects could be analyzed in terms of intra-cluster distances that is to be minimized so that I can really have a kind of cluster where the entities or the items are closely related. And the second is inter-cluster distance. So one cluster is distinct with respect to the other cluster. So typically I am analyzing the cluster, I'm doing the cluster analysis, and there are different types of cluster analysis techniques. One is partitioning clusters. So divide the data set into non-overlapping clusters. You can use k-means or k-medians. You have hierarchical clustering. This creates a hierarchical tree-like structure. You have agglomerative bottom-up approach. It starts with each data point as its own cluster and iteratively merges the closest cluster. For example, you want to group the warehouses based on geographical proximity for regional distribution network planning. Similarly, you have the technique like divisive, that is top-down approach, just the reverse. Start with all data point in one cluster and iteratively splits cluster into smaller ones. So typically in the supply chain, you want to break down a large product inventory into categories based on sales pattern and demand variability. The another clustering approach is density-based clustering. Typically, it is DB-CAN, density-based spatial clustering of application with noise, identifies cluster as dense regions separated by areas of lower density. For example, in logistics, you can identify the areas with high delivery demand concentration for setting up local distribution hubs. The another clustering approach is distribution-based clustering, or you can say Gaussian mixture models, GMM. It assumes the data points are generated from a mixture of Gaussian distributions, and typically you can use this approach in a supply chain where clustering of the demand pattern that are influenced by different market segments is highly useful. Various applications are there of cluster analysis: warehouse optimization, transport network design, supplier segmentation, demand forecasting, risk management, inventory management, and location analysis. So the steps involved: you define the problem in cluster analysis, then selection of the similarity measure, selection of the type of clustering, decide the number of final cluster solution, calculate cluster centroid and give a meaning to clusters, and finally assesses cluster validity and model fit, whether my analysis and clusters really have statistical significance or not. This is just the example where the clusters are created, a sample based on community, funding and support, publication, academic citizenship, and company relationships. You can conduct the cluster analysis using the various links posted here. Basically, you can learn how to conduct cluster analysis using SPSS. To conclude, this session has provided quite an exhaustive understanding on widely used statistical techniques, and this would really help you to enrich your researching rigor and deploy the right kind of method, right kind of approach, statistical analysis, considering your research quotient and scope of the research as the central part. So Gati Shakti Vishwavidyalaya is India's first and only university focusing on all modes of transport: rail, road, aviation, water, ports, and shipping, with a vision to reduce the logistics cost of India from 14% to 8%. It focuses on all types of educations: undergraduate, postgraduate, PhD, executive training, and it cuts across all three dimensions: technology, infrastructure, management services, and policy regulation. University operates with a vision, innovation-led, industry-driven university. It has a strong tie-up with various leading industries like Airbus, Nippon Koi, Nokia, Siemens, Jacobs, Plaza India, Railtel, and many others. Thank you for your interest in learning the various dimensions of faculty and student development. We will keep exploring more issues through this platform for the benefit of faculty, students, most critical entity in the higher education in India. Thank you very much.